Dr. Y. Sarada, Professor, Department of Mathematics, Anna University. Her area of specialization is applied probability and stochastic modeling. She has about 25 research publications in national and international journals. She has guided students for research projects. She has delivered lectures in her area of specialization in many institutions.
Welcome to the UGC lecture series on queuing and reliability theory. In the last lecture, we had seen the queuing theory. Presently, we would start with the reliability theory. What we are going to focus now in this lecture is a basic introduction to the reliability theory and then basic reliability concepts. One of the things which make life difficult is that we often rely on our own fellow men or even on ourselves. We expect from these people or from ourselves certain activities to be done in a given time, and when this time is over and things are not done as we expected, we are at the least disappointed. The problem of making a system reliable is basically an engineering problem. The development of science and technology and the needs of modern society are racing against each other. Industries are trying to introduce more and more automation in their industrial processes in order to meet the ever increasing demands of society. The improvement in effectiveness of such complex systems has therefore acquired special importance in recent years. The effectiveness of a system is understood to mean the suitability of the system for the fulfillment of the intended tasks and the efficiency of utilizing the means put into it. The suitability of performing definite tasks is primarily determined by the reliability and quality of a system. Failures are a way of life in the modern technological world, and the penalties paid by the people in terms of money, time, and security are becoming more and more severe due to the increasing application of complexities and automation. This does not mean that systems cannot be made more reliable. Better understanding of failures, improved manufacturing techniques, careful planning and designing of new systems, and proper selection of components are some of the approaches which can be tried to reduce the level of unreliability of systems. We will see few examples here. The impact of the failure or mismanagement of a power distribution system in a major city, the malfunction of an air traffic control system at an international airport, failure of a nano system, miscommunication in today's internet systems, or the breakdown of a nuclear power plant. Also, a space shuttle consists of hundreds of thousands of components. These components functioning together form a system. The reliable performance of the system depends on the reliable performance of its constituent components. So, things fail. For example, most of us in the last 1 or 2 years would have seen the following things fail. For example, washing machine fails, car battery may go dead, toaster oven, electrical plug burn, water heater may leak, USB or the TV remote control or the stereo amplifier quit functioning, an automobile engine starter fails, house roof may leak. The car battery, engine starter, washing machine, motor, these experiences wear out after a normal life. The toaster oven plug would be a poor design to withstand the amount of the current passing through it. The corrosion of the hot water tank may have caused it to leak. The corrosion may have been partly attributed to the lack of preventive maintenance. This is one of the important basics of reliability, which required periodical draining of the bottom of the tank. The TV remote control's failure may have caused by a random electronic component failure. On the other hand, the stereo amplifier failure may have caused by an open at a solder joint. Similarly, poor construction might have resulted in the house roof leaking. Some of these failures may have caused much inconvenience in addition to their economic impact. Several of these failures raise concerns about personal safety, although no injuries resulted from them. Many failures, however, are much more significant in both their economic and safety effects. We will see another example. The 1986 explosion of the Space Challenger was a result of the failure of the rubber O-rings that were used to seal the 4 sections of the booster rockets. The below freezing temperatures before the launch contributed to the failure by making the rubber brittle. So much of cost is involved in the making of such space shuttles, and the faults attributed to such thing like the failure which made the rubber brittle are very costly. In general, causes of the failures include bad engineering design, faulty construction or the manufacturing processes. Human error could have been a reason, poor maintenance, inadequate testing and inspection, improper use, lack of protection against excessive environmental stress. Now we will look into the basic concepts of reliability. We define, say, capital R as the unreliability of an unrepairable system, or the basic idea here to find a quantitative measure of what is called the reliability of an apparatus in daily life. We want to have a measure for the chances which are given that a system does not fail under given conditions during the time interval 0, t. Now we will see the definition of reliability. It is the probability that a component or system will perform a required function for a given period of time when used under stated operating conditions. It is the probability of a non-failure over time. Failures should be defined relative to the function being performed by the system. The unit of time must be also identified. Example, clock time, operating hours, cycles. Here a cycle could be the landing of an aircraft or a load reversal or turning on of an electric motor and so on. Sometimes reliability is not defined over time, but it could be over another measurement such as the miles travelled. The system should be observed under normal performance factors. For example, the design loads, which could be the weight, voltages, pressure. The environmental factors can be temperature, humidity, vibrations and the altitude. When I say the operating conditions, it could be the use, the storage, the transport and the maintenance. Reliability definition stresses 4 major elements, namely the probability, intended function, the time, the operating conditions. Time we saw earlier, intended function also we saw, the operating conditions just now we saw a few examples, and then the probability. So, wherever the randomness is there, probability comes into play. So, suppose we define capital T is the time till the failure of the unit occurs. It is a random variable, then the probability that it will not fail in a given environment before time t is given by capital R of t, which is the reliability function, is defined as probability of this capital T greater than t, small t. So, from this you observe that reliability is always a function of time. So, essentially here we are observing that this capital T is the time till the unit failure occurs, which is a random variable, because we are not knowing beforehand when the system would fail after it has been put into operation. So, basically here we are looking into the probability of the system failing without previous failures. In other words, it is the probability of the system failing for the first time, or it is like the system has survived small t units of time. It is of age t already. So, reliability is always a function of time. We observe that R of 0 is 1. What is the meaning of R of 0? R of 0 is probability that t is greater than 0. That is, the time until failure is greater than 0. Here we are noting that once the system is put into operation, we note that installation time as the origin, namely t equal to 0. So, we are asking for probability that the time till failure is positive. So, it crosses, it works more than 0 units of time, but this is a sure event. So, the probability is 1, that is R of 0 is 1, and similarly R of infinity is equal to 0. Again, going back by the definition, R of infinity is probability that capital T is greater than infinity. Mathematically, though, we are writing it as R of infinity is P of t greater than infinity. But then, is it possible that the time to failure of a system be greater than infinity, which is not a possible event, it is an impossible event. So, the probability is 0. That is why we have R of infinity is 0. And hence, we see that R of 0 is 1, initially it is 1, and R of infinity is 0. So, what kind of a function is this R of t? We already observed that R of t is a function of time. So, now with this range we have, namely R of 0 equal to 1 and R of infinity equal to 0, we see that R of t is a non-increasing function, that is a decreasing function between these limits. So, the graph will be tapering down as time increases from 0 to infinity. Next, reliability, it is the ability of the unit to maintain its quality under specified conditions for a specified time. So, the intended function of the device is related to the quality. So, quality also is a part of reliability. So, when you are able to identify the intended function, we are talking reliability in relation with quality. An example now, if an electric generator is expected to provide an output of 5 kW at 220 V under certain conditions, then the 5 kW output at 220 V is the intended function of the generator. So, when you are dealing with a system, we are to identify what the intended function is and what the probability could be assigned and so on. So, what is the time duration that we are talking about and what are the operating conditions? Because we already observed that reliability is based on 4 major elements, namely the probability, the time, the intended function and the operating conditions. So, here we saw an example about identifying the intended function of an electric generator. So, any deviation in either of these two output parameters will be termed as the failure of the generator. So, this may happen today or any time in future. Next, we will see these failures and failure modes. What is a failure? That is a fundamental question. The partial or total loss or change in those properties of a device such that its functioning is seriously impeded or completely stopped. Examples: switches, electric bulbs have well defined failures. A few devices, namely voltage stabilizers, resistors, etc., have a range of operating conditions. For example, the output voltage of a stabilizer may lie within the limits like capital V plus small v and capital V minus small v. The device is said to fail when the output voltage crosses either of these limits. Failures caused by events external to the component or the system, for example, environmental conditions such as hurricanes, earthquakes or excessive heat or vibration, will appear to be random. So, by this way we are coming to observe that failures can be deterministic and failures can be random. So, then how do you characterize this randomness? So, this randomness may exhibit a pattern that can be modeled by some probability distribution. So, by this way we are bringing into the probability theory random variables distributions into the analysis. Another important feature in the basics of reliability is maintainability. Maintainability is defined to be the probability that a failed component or a system will be restored or repaired to a specified condition within a period of time when the maintenance is performed in accordance with prescribed procedures. So, the maintainability is once again can be viewed as the probability of the repair in a given time. Thus, probability theory has been used to analyze the reliability of components as well as the reliability of systems consisting of these components. And reliability is defined in terms of a device which may be a component in a system or a system consisting of many components. So, a single unit system or a multi-unit system. Since the performance of a system usually depends on the performance of its components, the reliability of a system is a function of the reliability of its components. So, this is a very important feature to be noted, that is, the reliability of a system is a function of the reliability of its components. If we are talking about a multi-component system, then this is applicable. As observed earlier, time is an important factor in the definition of reliability. Time, we saw, it could be the clock time or it could be some kind of cycles, and cycles may depend on a particular event which is performed periodically or which occurs periodically. If a newly purchased device can perform its intended functions satisfactorily, what is the probability that it will last for a specified period of time? Say 3 years, how long will it last? What will be the life of this device? These are the kind of questions which are attempted fundamentally in reliability. So, as before, assume that capital T is the random variable representing the lifetime of a device. Because it is the lifetime of the device, it is continuous. The random variable is continuous and it can take only non-negative values. So, its statistical distribution can be described by its PDF, namely the probability density function little f of t, the cumulative distribution function CDF capital F of t, and or its characteristics such as the mean and variance. So, we have this capital R of t, namely the reliability function, which is defined as probability of t greater than t, which is equal to 1 minus capital F of t. This capital F of t is the cumulative distribution function, and by definition this function is written as using the probability density function little f of t as integral t to infinity f of t dt. This also has another name, the survival function or the survivor function. So, capital R of t is nothing but the survivor function. Another notation is also used in general, namely capital F bar of t. So, you have capital R of t, capital F bar of t inverts the survivor function, the survival function, all together they are all synonyms. We are talking about the reliability function, and we already observed that the reliability function is a function of time little t. So, this capital R of t is defined as probability that the device's lifetime is larger than t, that is, it is more than age t, or it is the probability that the device will survive beyond time t. In other words, this is same as writing the probability that the device will fail after time t. Mind you, we are talking about the failure happening for the first time once the system has been installed or put into use at say time t equal to 0. So, we are asking for the probability of the failure after it has survived for t units of time without a failure. It is the probability of the first failure happening after t, that is what we are asking here, because we are talking about reliability here. So, how reliable is the system? So, as observed before, R of t is called as a survivor function and the cumulative distribution function of t is called as the unreliability function. Both are complementary events, complementary functions. CDF of t is the cumulative distribution function, that is the capital F of t, and R of t is written as 1 minus of capital F of t, or 1 minus of the cumulative distribution function capital F of t. In other words, mathematically putting it, capital R of t is probability that capital T is greater than t, that is 1 minus of probability that capital T is less than or equal to t. So, we are once again talking about the basic fundamental quantities related to random variables. We also said earlier, other than the probability density function, the cumulative distribution function, the reliability function, we can also talk in terms of the expected value or the mean of the random variable t. So, that is what has been given here. It has a name. So, the expected value or the mean of the lifetime capital T is also called the mean time to failure, which is abbreviated as capital MTTF. So, any literature on reliability, you would definitely see MTTF. It is the mean time to failure. So, the expected life of the device, namely the mean time to failure, which is defined as expectation of capital T. Remember, capital T is the random variable which talks about the lifetime of a device. So, E of t is defined as the usual expectation definition, integral 0 to infinity t f of t dt. This is the usual definition of the expectation of a random variable t, whose PDF is given, probability density function is given by little f of t, and this is also equivalent to writing integral 0 to infinity capital R of t dt. This R of t dt is nothing but capital F bar of t dt, or this is 1 minus of capital F of t dt. So, this equivalency, this relation, I am giving it to you as an exercise problem. Please try and show that integral 0 to infinity t f of t dt is equal to integral 0 to infinity capital R of t dt. You have to do little simplification here. So, try this. As of now, what we have done in this lecture is, we have got introduced to reliability, different types of failure, namely the deterministic failures, random failures, their causes, and what is the need for the maintenance, and how reliability can be improved based on the various types of failures and their causes, and how the technological advancement is posing challenges to improve the reliability of systems. And as other basics of reliability, we saw the time to failure, the probability distribution functions, the cumulative distribution function, the survivor function which is nothing but the reliability function, and the mean time to failure in terms of the reliability function. In the next lecture, we will look into more details of the basics of reliability in terms of the hazard rate functions, lifetime distributions, and the mean time between failures with a few examples. And as an exercise, I want you to prove that integral 0 to infinity t f of t dt is equal to integral 0 to infinity capital R of t dt. Thank you.